When the intensity of vertical loading omega is constant, intensity of vertical loading the condition closely approximates that of suspension bridge where the uniform weight of the roadway may be expressed by the constant W, as shown in this picture. The mass of the curve itself is not distributed uniformly with the horizontal, but is relatively small, and thus we neglect its weight. For this limiting case, we will prove that the cable hangs in parabolic arc. We start with a cable suspended from 2 points A and B as shown in the picture, which are not on the same horizontal line. We place the coordinates at the lowest point of the cable here, where the tension is horizontal and is T0. Integration of this relation gives us omega on T0 T0 is constant, but we can obtain this relation plus C, which C is constant. Integration for the coordinate axis chosen, d by dx C equals to 0 at this point. So our relation reduces to another integration gives us this relation. Generally, you should be able to obtain identical results with the infinite integral together with the evaluation of the constant of integration. These equations give the shape of the cable, which we see is a vertical parabola. The constant horizontal component of cable tensions becomes the cable tension at the origin, inserting the corresponding values for X, LA, and HA. We can obtain T0 from the geometrical relations. The tension T is found from a free body diagram of a finite portion of the relation from this picture. T equals to T0 square and we had this relation before, T0 from the geometrical specification. T can be calculated as this relation as a function of x squared s. The maximum tension occurs when T max at x squared. We obtain the length SA of the cable from the origin to point A by integrating the expression. ds Also, we can integrate this expression in closed form for computational purpose. It is more convenient to express the radical as a convergent series and then integrated it term by terms. For this purpose, we can use this polynomial relation. We say that with integration, the length of the cable SA this cable or we can write LA approximate calculation. HA, LA, second, HA, LA, 4, the relation which apply to the cable section from the origin to point B can be easily obtained by replacing HA and LA SB HBLB HBLB 4 plus we can obtain the length of the cable. For a suspension bridge where the supporting towers are on the same horizontal line, we have an expression for this type T max equals to L omega on second as LA 1 plus N on 4H a square, and the length of the cable can be calculated as this relation 1 plus 8 This series converts for R values H on L in most cases H is much smaller than L on 4, so that the 3 terms of the equation give a sufficiently accurate approximation. For the previous calculation, the convergence is L, A on H, HA on LA, or HB on LB smaller than 1 second. The next type of cable is catenary cable.